Hello everyone and welcome to our video today on partial fraction decomposition. Partial fraction decomposition sounds like a very complicated thing in mathematics, but in fact it is not. Let's start by talking about what is partial fraction decomposition. What we want to do in this section is to start with rational expressions and ask what simpler rational expressions did we add or subtract to get there. This process is called the partial fraction decomposition of a rational expression. Think about adding these two fractions together here. By now, we should all know how to add two fractions together. We get a common denominator, we combine like terms, and there we have it. The question for today is, how do I get from here to here? How do we find the parts that make the single fraction the partial fractions? Why would we want them? Well, there's really only one thing that I can think of that uses this in mathematics, and that would be in integral calculus. We would need to do this in order to do some integration, which you'll get to in a few years. There are four different types of cases that we can deal with when we're talking about partial fraction decomposition. Case one, we're going to start with here, is the easiest one. It's a non-repeated linear factor. What does that mean? That means that the denominator has something like this in it, or like this, or even like that. Anything that is a linear factor that is not repeated. If a linear factor appears in the denominator and is not repeated, it gets a constant numerator. We'll look into that more when we get to step two. But first, the first thing you're going to always want to do is make sure that the denominator is in completely factored form. All right, so I'm going to rewrite f of x here. The numerator does not need to be factored if it can. Just leave it exactly as it's written. But the denominator you want to factor completely. This is going to factor to x plus 4, x plus 5. Which means there are two non-repeated linear factors in the denominator. So both of those are called case one for partial fraction decomposition. All right, so now step two here, I'm going to write one partial fraction for each of those factors with the unknown constants. They get a constant in the numerator. All right, so now I can say f of x is equal to a over x plus 4 plus b over x plus 5. A and b are some constants that we don't know. All right. Just a quick side note here, if you happened to factor this denominator as x plus 5, x plus 4, then this would be a and this would be b. It doesn't matter. Your final answer in the end is going to be exactly the same. Okay? Step three is to multiply through. What do I mean by through? I mean, if we set this equal to this, because they are equivalent after all, and we multiply everything by the common denominator. So all this gets multiplied by x plus 4 times x plus 5. So then the denominator on the left side cancels out. We're left with 3x plus 10 equals a times the x plus 4's cancel, so x plus 5, plus b times the x plus 5 cancels times x plus 4. Simplifying that, we get 3x plus 10 equals ax plus 5a plus bx plus 4b. Step four is to set up a system of like-term equations. So, how many equations do you need? Well, however many variables we have. And by variables, I mean not x. I mean a, b, c, d, e, those variables, okay? Or you can think about basically how many terms you have on the left side, the highest term all the way down to a constant. So if it was an x cubed, you would need 4 terms. If it was an x to the 5th, you would need 6 terms. Since this is an x to the 1st, you would need 2 terms. So we're going to go 3 and 10. We're just looking at the constants here. So 3, I'm going to do some highlighting here, 3x would equal ax plus bx. So 3 must equal a plus b. 10 is a constant, so that must equal our other constants. So that must equal 5a plus 4b. Now in this unit, we've looked at a lot of different ways of solving systems of equations. At this point, you can use any method that you want to solve this system of equations. All right, so for this one, maybe just be easy here to multiply this by -4 and add through. So we get -2 equals a plus 0b, or just a equals -2. So 3 equals -2 plus b, 5 equals b. So we've solved the system. So then finally, our final answer here, we're going to rewrite f of x like this, but putting in a and b. So it's going to be -2 over x plus 4 plus 5 over x plus 5. And if you were to add these two together, you will get back to here. All right, at this point, I would encourage you to pause this video and try the problem on the next slide, g of x. Unpause it when you have completed it. All right, here is your work and answer for your practice problem. Let's move on to case 2, a repeated linear factor. So you could still have a non-repeated linear factor, but then you also have a repeated linear factor. So what do we mean by a repeated linear factor? That could be x squared, or x plus 2 squared, or x minus 4 squared, something like that. Or even x plus 8 to the 6th. Could be anything like that. Anything where the degree is higher than 1. Well, right now, we don't have a factor that's higher than 1, but let's take a look what happens here if we factor the denominator. This would factor to x minus 1 times x minus 1, or x minus 1 squared. If that's the case, you're going to set up partial fractions like this. The first degree linear power gets a constant, but also every power up until the last power also gets a constant. So let's just say this was a 4 here. We would do x minus 1 squared, x minus 1 cubed, x minus 1 to the 4th. But since it's just squared, we stop here. Now we're going to multiply through by our common denominator, and we get 7x minus 10 equals, the first one of the x minus 1's cancels, so we're left with a times x minus 1. In the second term, both x minus 1 cancels, we're left with plus b. So 7x minus 10 equals ax minus a plus b. Set up our system, which again is going to have two equations because we have an x and a constant. So our x, that's just a, and our constant is -a plus b. All right, well, this is a real easy equation to set up here. All right, we already have a, it's done. A is 7, right? So then put 7 in here. We get b is -3. So our final answer there then for h of x is just going to be 7 over x minus 1 minus 3 over x minus 1 squared. You could also write plus and negative, but that just doesn't look right to me. So minus 3 over x minus 1 squared. Pause the video again here and try the next one, j of x. Come back when you're done. Here is the answer for number 4, or fourth problem here, j of x. Should look something like this. Which brings us to case 3. If we have a quadratic non-factorable factor, we have to conclude a partial fraction with a linear component on top and a quadratic component in the denominator. So let's take a look at this f right here, f of x. First thing you want to do is try to factor the denominator as much as possible. And it's already completed. There is no factoring this any further. So this right here is case 1. This is a non-repeated linear factor. This is case 3, a non-repeated quadratic factor. All right, so the non-repeated linear factor gets a constant. We'll call it A. The non-repeated quadratic factor gets a line, bx plus c. And from there, we do exactly the same thing that we've been doing so far. Multiplying through on the left side just cancels out my denominator. The right side, we have a times this plus bx plus c times x plus 1. So distributing here, I get ax squared plus 2ax plus 4a plus bx squared plus bx plus cx plus c. And that's going to equal 3x squared plus 6x plus 9. So now we're going to need 3 terms, a squared, a first power, and a constant. So I have 3 terms, 3 equations. Squared, first power, constant. So x squareds, right? We have the x squareds. 3 would be a plus b. Sometimes it helps me if I cancel them out when I use them. First power terms, 6 would be 2a plus b plus c. And then 9 would equal 4a plus c. All right, so now we have a system of 3 variables. Again, we've learned a lot of different methods for solving this system. You choose what's best for you. All right, what I'm going to do here is I'm going to use 3 equals a plus b, and then I'm going to use these 2 to get rid of the c's. I'm going to subtract the bottom equation. So I have 6 minus 9, which is negative 3. 2a minus 4a is negative 2a. b minus nothing is b. And then the c's cancel out. Now I have a 2-variable system, 2 equations. All right, now if I subtract this equation, I get 3 plus 3, which is 6, a plus 2a, which is 3a, b minus b cancels out, divide by 3, I get a is 2. Put that back into maybe this equation here, 3 equals 2 plus b, b is 1. And let's go back to this equation here. Oops. 9 equals 4 times a plus c, c is also 1. So now I can write my final answer out here. F of x equals a over x plus 1 plus 1x plus 1 over x squared plus 2x plus 4. Once again, take a moment, pause the video, and try the 3rd practice problem here, decomposing p of x. Now it's already in completely factored form for you. You just need to go ahead and start solving it from there. Here is the answer to the 3rd practice problem. Which brings us to our last case. So our final case is a repeated quadratic factor. Okay, so if we have a quadratic factor, it's not factorable, and it's repeated. Basically, we're going to have to combine cases 2 and 3. Okay, so we're going to have every power from the highest power down to 1 is going to get its own partial fraction. But since these are quadratic, they get linear terms up top. So now when I multiply through I get x squared plus 15 equals the first term, I'll multiply that once by x squared plus 3. The second term both cancel out, so just cx plus d. Now, I'm going to go ahead and simplify that right side. So ax cubed plus bx squared plus 3ax plus 3b plus cx plus d. Because I have a cubic, I'm going to need 4 equations this time. Cubic, squared, linear, and constant. On the left side, there's no cubic, there's 1x squared, there's no linear, and there's 15 constant. On the right side, there's a cubic, there's b squared, there's 3a and c linear, there's 3b and d constant. All right, so now this looks like it could be a pretty daunting system to solve, but it's actually not at all. In fact, 2 of the 4 are already solved for you. A is 0 and 1 is b. So then here, 0 equals 0 plus c, so 0 equals c. And here, 15 equals 3 plus d, so d is 12. And that's it. We have our answer. M of x can be rewritten as 0x plus 1 over x squared plus 3 plus 0x plus 12 over x squared plus 3 squared. So one last time today, you can pause this video and try the last practice problem. When you're done, come back and check your answer. Here is our final problem of the day. That'll do it for our video today on decomposing partial fractions. Thanks as always for watching, and we'll see you again next time.